Okay, welcome to lesson 2. We're going to talk about data visualization. So this is you've collected your data. Now you want to see how that variable is distributed. So we're going to start off in the scenario where we have categorical data. So when you have a variable that's categorical, there are a couple of plots in particular that we tend to use. So for example, I could survey 100 people and record their eye color. So I have 100 people's eye colors written down. I could survey 500 people. I can ask them who they voted for in the last presidential election. And as the idea is that you can take each of these and you could say, okay, well, brown eyes, blue, whatever other colors, and you can have a category and a number in each category. And that is the idea we're going to run with when we make our visual. Okay. So when we have a categorical variable, they can be numerically summarized using counts, percents, or proportions. We usually stick to proportions a lot of the time. So a population proportion, that would be looking at the proportion of units in a population with a specified characteristic. I could be interested in, for example, the proportion of all OSU students with brown eyes. So the numerator here is going to be all the OSU students that have brown eyes, so whatever number that is, over capital N. Capital N is for the number in the population. And the symbol we use is just the letter P. Now if we have a sample, because often we don't have access to population data, it's going to be the proportion of units in the sample that have that specified characteristic. So the numerator is now the number of units in the sample that have the characteristic divided by the number in the sample. So suppose I take a sample of 20 OSU students and I count how many of those have brown eyes. The number in that sample that have brown eyes over 20 because I sampled 20. And for notation here, this is a P with a hat. It's got that caret on top. It's a P hat. So we tend to write P hat. So frequency tables, those are also common just to summarize what we have. So it lists all the categories and it provides a count or proportion or percent for each individual category. So, for example here, we took a sample of hospitals in a large area, and we went ahead and we recorded, okay, well, in this year, in 2015, how many babies were born on Sundays? So 714 babies were born on Sundays. 1,145 were born on Mondays, and so on. So I have 7 categories here, and I have the count. I also have the percent. So this would be my frequency table. Now to visualize, that's usually our next step. A table's handy, but it's not necessarily as powerful as a visual can be. So the first one we're going to look at is a bar chart. Out of the two that we have, the two types of plots we use for categorical variables, statisticians tend to like bar charts. Notice a bar chart is the same as a bar plot or bar graph. It means the same thing. So each category gets its own bar. So same data from before. So Sunday, Monday, Tuesday, Wednesday, all the way through. In this case, we put them in order that those days are on the calendar. If you do it by counts, if you add up the heights of all of them, it should be the total sample size. Versus if you do it by percents, these should add to 100%. Every once in a while, just because of rounding, it's a tiny bit off, but if you don't use rounding, it should be exactly 100%. So when we make plots, it should have a title. So births by day of the week in 2015. It should have some sort of label here, so maybe day of the week. And here, these are counts. So the thing that's cool about bar charts is with these categories, I can have them in this order, but I could also change the order. So here, this is the same frequency table data, except now I've reordered it so the highest count is first, then the second highest, all the way to the smallest. So this way I can easily visualize, okay, well, what days were babies born on the most frequently? And it looks like Tuesdays, Wednesdays, Thursdays, Fridays, Mondays, Saturdays, Sundays. It looks like people, at least in this area, did not have their babies on weekends as often, which is interesting. So that's what they mean. The categories, they can be reordered to enhance comparison, to make it maybe easier to see like where the most was and where the least was. So here's some other examples of bar charts, some uses. A lot of times folks will have years. Most of the time people aren't going to reorder years, but they can. Same with months, you can do that as well. In this example, people are looking at hazards for driving and car accidents. And so they decided they wanted the highest risk at the top and the lowest risk here. So just examples. Definitely we've seen lots and lots of bar charts in our time. Whether or not you've done any stats, they're out there. The other one that comes up a lot, and we have to really mention, are pie charts. And I say we have to mention it. Statisticians don't particularly like them. However, they're very, very common. So each category is represented by a slice of this pie, right? I mean, I'm not sure it looks like a pie here, but. So the sizing of each slice is in proportion to how much of it takes. So Saturday, 10.7% of the babies were born then. So this slice, this dark blue slice, is 10.7% of that entire circle. The percents should add to 100%. One thing to note is if you use rounding, sometimes it doesn't add perfectly. If you don't use any rounding, it will add to 100% exactly. And then once again, you should have title, so birth by day of the week, and category labels, so every single category is labeled here. Some people might use a key or a legend and have the colors off in a corner. And then you should have count or percent or proportion. It should be clear there. So our warning though, pie charts are very common. You will see them everywhere, but they can be a very poor visual display. They can be misleading. So how can they be misleading? I wanted to show, here I have 3 pie charts, and they're all the same pie chart. This one is looking straight down, this one's looking at an angle from a certain height, this one's changing it. If you even decide to focus on just this yellow sliver, it doesn't look, just at a glance, to take the same amount of space in all 3. And that's the problem, that it can be misleading. It's very, very easy for a pie chart to be misleading this way, because you can change the angle and the height and whatnot. Some folks, they might do it intentionally, other people won't, but it's still easy to mislead. So there are 2 types of graphs that we'll use for categorical data, and a cheesy way that I like to remember. So referencing How I Met Your Mother TV show, I don't even know, a few years ago it ended. To remember the plots and graphs for categorical variables, there's an episode where this character Marshall gets really, really into printing posters, and what he says then is, this is a pie chart describing my favorite bars, and this is a bar graph describing my favorite pies. So these are the 2. Bar charts and pie charts, those are the 2 for categorical data. So now quantitative data, and there are a lot more options for displaying quantitative data. We are going to focus on 3 of them in particular. So when you have a quantitative variable, there are different ways. You're not going to use a pie chart. You're not going to use a bar chart. Also know, if you ever see this phrase, a time plot, nothing that we study in Stat 201 is going to use a time plot. Just know that. So for example, before I was looking at categorical, now it's quantitative. I survey 1,000 people and record their heights in inches. So I have 1,000 heights. It's quantitative. I could average it. This is a quantitative variable. I could record the daily screen time in minutes of 400 students. I mean, realistically, that would be a nightmare to actually coordinate, but it could be something someone collects. So there are a lot of options for graphs that we have here. But in this class, we're going to focus on histograms, stem and leaf plots, or also stem plots, and box plots. So visualizing, this is a largish data set to be putting in by hand if you're using a calculator. So here, it's really just, it was way too long to have in one set. We have 50 US states here. They just use the standard 50. So these acronyms are states. So CA is California, OR is Oregon, that kind of deal. And the percent here, it represents the percent of students who stay in state for their first year of college. And this was in one particular year. So, I don't know, let's say 2016, I don't know. So in 2016, they did a survey, found that in Alaska, 83% of students stayed in their home state of Alaska their first year of college. So, histograms, it's going to show a quantitative variable by using bars. So, beware is different from a bar plot. And we'll go over why. So then stem plots, so raw data, we put them into stem and leaves. This might be a throwback to a math class in high school. Box plots. And data summary features are displayed as a box. We have a tendency to make very, very oversimple names sometimes. Box plots, pie charts, bar charts, that kind of idea. We also have dot plots. They're made of dots. So a stem plot. So looking here, it shows the distribution using raw data. I wouldn't recommend using it for a very large data set. It's kind of tedious. If you have a large data set, people tend to prefer histograms and box plots. So it separates each observation into a stem and a leaf. And we will practice this, although not with this exact data set. So the stem is the first part of the number. So if I have the number 36, and I were to draw a line between, this is the ones place and the tens place, my stem is 3, and my leaf is 6. That's the idea. So it organizes into a vertical column. So here are all the tens places in here. And there should be 50 observations. Usually, I like to write commas in between. They didn't here. It's not the biggest deal. But know that some folks will use commas. And then often if you wanted to look at how it was shaped, you'd almost kind of turn it up on its side. So you go, oh, look, I have some lower here, some higher here. That's part of how you would look at it. Half the time if I'm in class, I tilt my head to the side. It's just kind of how a lot of us do it. So we are going to use a much smaller data set. We're going to start off, we have 201 students from an old term, and then we ask how long they exercise each day in minutes on average. So like this student said they exercise 26 minutes on average. This one's at 103 minutes on average. So the first step to do is to rewrite all these numbers in ascending order. So from smallest to largest. You might notice I already did that, but a lot of times we will give it to you all mixed up. So the first step to do is going to be writing it in order. So once you do that, you separate each observation into a stem and a leaf. So like here, my stem is 2, my leaf is 6. And I can do this with all of them. 2, 8, 2, 9. And I'm going to do this with all 20 observations. I have a tendency to even write the stems first. This one's the tricky one. 103, you're going to have a stem of 10 and a leaf of 3. So 34, 5, 7, 0. Okay, so I have this step down. The next thing I'm going to do is I'm actually going to go ahead and arrange the stem plot there. I'm going to write all these stems vertically. So looking here, I'm going to start in the 20s and I'm going to go all the way to 10. So here, 20, I had 30, 40, 50, 60. I didn't have any observation in my 70s, but I need to include it. I'm just going to leave it blank right here, but you must include everything all the way up to the highest one. So there are all my stems. So here, sorry I'm peeking at a paper because I can't remember, off the top of my head. It's a lot. So I tend to write commas in between. You don't technically have to, but these should be in ascending order. So 26, then 28, then 29. And then 30, 30, 1, 3, 4, 5, 7, 40, 5, 7, 7, 9. I think this is 53. I'm trying to read my writing. Sorry about that. 62. Then, like I said, we didn't actually have any observations in the 70s. So you skip over it. You just leave that particular row blank. 85. Same with the 90s. We didn't see any observation in the 90s, so we just leave it blank. But you still want to include it. Because if you don't really get to see how the observations are spaced out. So there you go. So here, now that we've done it, so our vertical line, we drew that. We drew the stems and then the leaves there. And then it should have a title. So stem plot, exercise times, I guess student exercise times, 2014. And then by legend, this is just to say 26 is equal to 2. This is a vertical line, 6. Because some folks, they might not put it between the 1s and 10s place. They might put it somewhere else. We are always going to put it between the 10 and 1s place. So that is going to be our stem plots. Next are histograms. So these are really, really popular, especially if you have a very large data set. So one of the things you do, yes, it does have bars. You divide the data into classes or bins of equal widths. So you might decide, here, I'm going to take, bins of 10. So from 30 to 40, from 40 to 50, 50 to 60, that kind of idea. Somebody decided ahead of time that each of these tick marks would be 10 apart. And you could have picked any number, but they picked 10. 10 is pretty popular. And then the height, this frequency is going to say, oh, well, how many times did I see it? Like there was an individual, was it Alaska, had 36. So but between 30 and 40, there was only one observation in the 30s. Yeah. So things to note though, a big difference between bar plots and histograms. Look at what's on the bottom. So looking here, these are percents in state. It would not make sense to rearrange these. You wouldn't put 90 to 100 here and 30 to 40 here. Their percents, it goes specifically in this order. You're going to want to stick to this order. It's a histogram. So if it's this quantitative thing and you can't rearrange the bars reasonably, it's going to be a histogram. If you can rearrange the bars because they're categories and it doesn't matter what order they're in, it'll be a bar plot. Okay, so back to our states and in-state students example here. I'm going to make a histogram. I've decided to make bins roughly groups of 10 here. If you've noticed, all these percents, they're rounded to the nearest percentage. And not only that, if you look here, Vermont is the lowest one. So I'm going to start with 31 to 40. Absolutely, you're welcome to do 21 to 30 and the lower ones. However, since I know Vermont is the lowest one, I'm going to start here. And then I'm going to include all the others. So 41 to 50, 51 to 60, all the way through 91 to 100. I stopped at 100 because you can't have more than 100% of your students stay in state. It doesn't work that way. So frequency, for ease, I went ahead and I used some highlighting here. So looking in the 30s, we only have Vermont. In the 30s, we have 1. So frequency is 1. Now I'm going to look in the 40s, well, 41 to 50. I only have 1, so it looks like Rhode Island. There we go. So now 51 to 60, looks like 4 of them. So 4. 61 to 70. So I have 4 in this first column, 1, okay, so 7. Absolutely take more time. I think I did this color coded when I did this on paper. So then 71 to 80, there's a lot more there. There's 2 here, 6, 3, 3, 14, I think. 81 to 90. It's 5, 5, 5, 3, 18. Maybe. And then 91 to 100. I'll find out on the next page. I have them on the next page, the correct frequencies, so 5. So here, if I add all of these up, I should get 50 because in this particular sample, there are 50 states. So that is one way to quickly check your work here. So here, okay, yeah, it was 18 there. So I have my bins. I have my frequencies, and I can go ahead and use them. So 30, I'm just going to draw a flat line at 0. So 31 to 40, so I have 1 of them. So I want it to line up with 1. So there's 1. There was 1 from 41 to 50. There were 4, so I'm trying to line it up here. 61 to 70, there were 7. Not drawing with a straight edge, so these bars might look a little lumpy. 71 to 80, there were 14 of them. 18 from 80 to 90. And then 5 from 91 to 100, so. And this is just kind of eyeballing it. Notice that I did pick bins that went from 31 to 40, 41 to 50. I could have chosen different bin sizes. So let me see how that goes. I'm kind of close. So if I instead use bins that went from 31 to 35, 36 to 40, so I have like bins of 5, it could definitely change the appearance of this histogram. So here, this is me using that bin width of 10, so from 31 to 40, from 41 to 50. If I had changed instead to 5, it still kind of has this shape, but it has a kind of bounce shape there. So it can noticeably change how it looks if you change the bin size. So just keep that in mind. And it's definitely a balance. You don't want your bin sizes to be too big. Like, you wouldn't want to have a bin from 30 to 100. It would just be one giant rectangle. That would look really, really weird. So describing distributions. So there are a few features of distributions we really like to pay attention to. So the first we're going to focus on is the shape. So we want to know the overall pattern. This means, is it symmetric or skewed? So if I were to fold in half, does it fold neatly in half, or is it really unbalanced? That kind of idea. And number of peaks. So does it have one peak? Does it have more? And we'll have a slide that goes specifically on that. We're also really interested in center. We want to know what a typical value is. So the center or typical value, where are, most of the observations concentrated a lot of the time. And usually we end up using like a median or a mean. And then spread. Spread's really important because if it's really widely spread, describing the center alone is not very useful. So we want to know how much it varies. So you can talk about the range. We're going to talk about IQR. I think it's a couple lessons from now, and the standard deviation. So range is just your max minus your min. And then it's also really important when you have these distributions to describe outliers. So you want to know oddball points. So they're extreme values that don't fit in with the rest, like they don't fit the pattern of the rest of the values. Or they are just so much further out than the others that they're worth noting. Note, you want to comment on the outliers, but unless you have an extremely good, non-statistical reason, like that, we have an outlier in our state's case, and it turns out that's because that one was, from Germany and not the United States at all, then you could throw it out. You can't throw it out just because you don't like it. So describing, we're going to go off shape first. So symmetric, the idea is if you drew a line right down the middle, it would fold roughly nice. Like you have one half, you have another half. It's roughly symmetric. It's a mirror image of each other, roughly. So then left skewed. It can be called negatively skewed. I'm going to stick with left. So if you thought of like, here's a tail, I don't know. It's a rat. I don't know. So this is a left tail, right? It's smaller on the left. Then it's a left-tailed or left-skewed distribution. It means that you have more values on the right-hand side. You have more high values and lower and less lower values. Right-skewed is pretty much the opposite. So this means that my tail now over here is on the right. It means that the bulk of stuff is down low, but then you have some values up high. And you could often, salaries for companies are going to be right skewed. You have a lot of people making minimum wage or lower money. And then you have, CEOs up here, something like that. Salaries are usually right skewed. So then one just quick way you want to check, is it right skewed or left skewed? So you can go ahead, use your hands. This is a little more fun in a classroom because we all stick our hands in front of each other, in front of our face. The idea is if you hold your palms towards yourself like this and you pretend that your thumbs are the tails, it's roughly symmetric if you have both hands out. If you, the tail is on the left-hand side, it's left skewed. On the right, it's right. So a lot of times I've seen, even during exams, people hold their hands out in front of themselves. Totally acceptable. It might be a nerdy way to remember this, but it's a way to remember. So I welcome you to it. So number of peaks. A lot of folks are really concerned with the number of peaks. Unimodal, you could say it has one mode or one peak. So this would be an example of unimodal. It has one peak. So if I were to fit that, it has a peak right around here. And that would be unimodal. If I were to look, however, at this is like bimodal. And I like to exaggerate just a little bit. If I were just looking at this half right here, I'm not worried about this. This is just some bumps. I don't think that's bimodal. This right here is just a mode right here. But looking at them together, that's two of them. I like to bring up that Dracula that Keanu Reeves was in. Bimodal is Dracula's hairdo. So it's going to be real exaggerated. It's not going to be like really hard to tell the difference between unimodal and bimodal for us. We're not going to try and be subtle there. So putting it all together, we want to remember talk about the shape. We want to talk about outliers. We want to talk about spread and center. So back to that example, percent of students who stay in state for college for those 50 states. If you put it together in a sentence, the percent of first-year college students that stay in state. So the first thing we listed, this is the variable. It's left skewed because, yeah, looking here, it's a left tail. Ranging from. So I don't know the IQR or the standard deviation here, but I do know the min and I do know the max. Well, the max. So the range is just the max minus the min. So it's 92 minus 36. So you could actually go ahead and do the math and find the range. But here we just said it ranges from this min to that max, and that's fine. With most states ranging from. So it's saying, hey, it's centered somewhere between 70 and 90. And that's okay. It's not super precise, but it's precise enough. You're looking here, between 70 and 90 is reasonable for a center. So centered roughly about 80%. So yeah, I'm guessing it's right there. And you can, from this, you can find the median. It's a little tedious with a stem plot with 50 observations, but it's something you could do. So here's another example. This time we took the weights of football players for the Seattle Seahawks. So up in Washington, the Seahawks, and the 2015 season. So took all of their weights in pounds. Here's their stem plot of those weights. And just looking here, I would argue, that doesn't look unimodal. I would even argue there's about two peaks. So if I want to put into a sentence, I need to put the entire, so the weights of the 2015 Seattle Seahawks range. So there's they range from 177 to 345 pounds. 167 to 345 pounds. It is bimodal. I'd say it's bimodal. And when it's bimodal, you're going to probably just say where each of the peaks are centered roughly. So this one, it's about 215. And it's okay if you give a range. And this one's about 300, roughly where it's centered. The typical weight, this one would be harder to do with it being bimodal. Chances are they probably just took the median here. Is most likely around 240, so it's probably somewhere around here. And that's harder to tell with bimodal. Most of the time if it's bimodal, we don't do a lot of the analyses that we do. Most of the things we have, it's going to be close enough to unimodal for our uses. And this is one of those times where when I'm in a class, I tend to ask folks, hey, is there any reason we might see two separate peaks here? Well, if you're familiar with football, they have an offense and a defense. And a lot of times, those two teams within a team weigh very differently. You're going to have players on the offensive team play way very differently than players who are defensive players. So that is likely contributing. You might want to look at those players separately. A lot of the times that you get multiple modes, so bimodal, trimodal, and so on, a lot of the times it's because there's some sort of grouping that you missed. Okay, and to finish up here, I want to say we have a few more slides. We want to be able to read a histogram. So if we give you a histogram, we want to be able to answer questions regarding like counts and proportions. So here, we have 138 students in a ST201 class. We went ahead and asked them how many minutes per night on average did they spend sleeping. Goodness knows I would probably round this number if somebody asked me. So we asked these 138 students, and we want to know, so here's the histogram, how many of them reported sleeping between 360 and 420 minutes per night. So 360 is right here, and 420 is right here. We want to know how many slept between. So here it just wants to know how many students. So I'm going to try and line things up here. Let's see. So looking here, I would argue that looks like 17. This lines up here. This looks like 8. So 17 plus 8. So 25 of the 138 students reported that they slept between 360 minutes and 420 minutes. So that would be our solution here. So absolutely super important. One of the things that is super useful is to be able to read and line up the frequency axis there. Also, definitely mark like 360 and 420. It makes it a lot easier to know where you're looking. So then we're going to progress from there because I found that 25 of them had between 360 and 420 minutes of sleep. But 25 out of how many? So looking at a proportion. So the total number of observations within that range over the total number of observations in your data set. So another example problem, I don't think it'll be the sleep. So this time around, we have 40 vehicles. It's the same make and model. They're given a tank of gas, and then they go ahead and have the car drive. I'm thinking around a track. It really wouldn't be great if they were driving around town. And they drive until the car stops, and they record how many miles that the car went on one tank of gas. So 40 cars. If I want to say, okay, well, what proportion of cars, so in this sample, drove more than 305 miles? I'm going to find, okay, well, 305 miles is right here. And so I want to know, I'm going to say p hat. It's a proportion, but it's a sample proportion, right? Because I have a sample of 40 cars. So it's equal to, what goes on the bottom is the number in the sample. So the number in my sample, it's 40. There are 40 vehicles. So then to find out what goes in the numerator, I need to add up, I want more than 305 miles. I need to add up these three bars. So I need to find the height of each one. So this one, it looks like it's 7. That one looks like it's 5, 4. So 7 plus 5 plus 4. Give you all a second. My 4 looks pretty curly. There we go. So 16 out of 40, 4/10. So 0.4. I like to put the 0 in there. If you were talking percent, this is the same as 40%. So 40% of the cars in this sample drove more than 305 miles on 1 tank of gas. So then for part B, I'm going to erase this here. It said what proportion of cars drove less than 280 miles. So 280 miles is right here. So less than it goes this way. So I need to count up these 3 bars. This is still a p-hat because it's a proportion from a sample. And it's still over 40 because the sample size is still 40. But now I need to add up these 3 bars. So this looks like 2, 1, 1. So 2 plus 1 plus 1. Get 4 over 40. So you go to 0.10, or if you had it in percent, it's 10%. So it's saying that 10% of the cars in this sample drove less than 280 miles on 1 tank of gas. Okay, so that is going to be our lesson 2. The next, we're going to start talking about measure of center, and then from there we're going to talk about measures of variance and spread. So we will check in. I believe we'll start that next week, in week 1.